After learning subsequences, let's talk about subsequence convergence theorem. This tells us that if a sequence x sub n of real numbers converges to a certain value x, then any subsequence of that sequence denoted by x prime or the sequence x sub n sub k of x also converges to the same limit. Previously, we're able to identify subsequences of a certain sequence. We're just going to list elements of the sequence and make sure that it follows a certain order in increasing manner. Okay, and we have identified even more than one subsequence. At this time, this theorem tells us that if our sequence is convergent and it is converging to a certain value, then any of those subsequences of that certain sequence should also converge to the same limit. We will illustrate this with an example on the next video, because for this video, we're just going to show the proof of this. Okay, to show the proof of this, of course, since we talk about convergence, we need to show the definition of a limit and show that for this subsequence, it also converges to the limit of x being the limit of the original sequence as well. So here is the proof. Let a certain epsilon be greater than 0, and let k of epsilon be present such that, okay, if n, a natural number n, is greater than or equal to the k of epsilon, then, okay, since we were able to, we are trying to establish the conditional statement that it converges to x. So then, x sub n, or the absolute value of x sub n minus x is less than epsilon. This statement is actually following the conditional statement here that, the condition where our certain sequence x sub n converges to x. Take note that this is our sequence, this is our limit, and if the absolute value of the difference is less than epsilon, then the limit of your sequence is this. Okay, that's the further expression of that before was this. Okay, this being the limit of whatever with the function, but in this case, since we're talking about sequences, we're using that. So let me erase the rest of the scribbles here, and we are trying to let that or assume that, because that's the part of our first part of our statement or a theorem. We need to show then later on that this is also true for this x sub n sub k minus x should also be less than epsilon, so that the limit of the sequence is also x, as this is what we're also trying to show here. So we will go to that later. Now, second part of here is the idea that since n sub 1 is less than n sub 2, less than n sub 3, okay, we are going to establish this so that we can invoke here the idea of increasing sequence is a strictly increasing sequence. Okay, we would like to establish that so that we can now say, by mathematical induction, we can further say that whatever would be our n sub k, this value here, this is greater than or equal to the value of k. Why? Because take note, this is strictly increasing. We don't know the given notation or expression for the sequence or of this, but this is a sequence of natural numbers. So whatever will be the value of n sub k, this is greater than or equal, if it's by 1, to our k. So you can actually show that using mathematical induction, but let's not do it here, as we would like to establish this idea alone. Okay, now that we are here, because again of the idea of strictly increasing sequence, then we can now here say hence, if k, this value, is also greater than or equal to k of epsilon, capital K of epsilon, we also have, okay, our n sub k, which is already identified here as greater than or equal to k. And since this is greater than, if we're doing that because that's actually again the part of showing limit, okay? So we'll have it here. So converging to, when you say converges to a certain value, so we're talking about limit. So combining the two inequalities, you have greater than or equal to the k of epsilon. I'm going to remove the middle man here. So we'll have here, so that I only have n sub k is greater than or equal to k of epsilon. So since we have established this, going back to the previous statement, once we were able to establish that x sub n minus x being the limit here is less than whatever epsilon is. So with that here, then using this idea, we can now say that x of n sub k minus x is also less than epsilon. By the way, we're going to look again here with this. So we're just changing this to n sub k, so that's why you have n sub k here, following the structure of the definition. So since we were able to establish that, we can now say, therefore, the subsequence x sub n sub k also converges to this limit x. So whatever would be the subsequence of the certain sequence here, as long as that original sequence converges to the limit of x, all of those subsequences should also converge to x, as this is also guaranteed by this proof. Okay, so this is the proof of the subsequence convergence theorem, which tells us again that if we have a sequence that converges to x, whatever would be subsequences that can be drawn or drawn out or illustrated from the said sequence should also be converging to the same limit x. Thank you very much for watching.